Hello, this video is entitled Iterated Integrals and Area in the Plane. Now, just like you can take derivatives with respect to certain variables, partial derivatives, you can also integrate respect to variables. So let's take a look at this particular integral. It has 3x squared y dx. So dx indicates that x is your variable of integration, so y would operate just like a constant as the 3 would. So the antiderivative, you're basically taking the antiderivative of x squared dx, which would be 1/3 x cubed, but that 3 would kill the 1/3, so that's why there's no 3 here. X cubed y plus c of y. Now, the c of y means that in this idea, not only can you have a constant c like we do for regular integration, any variable of y would also be considered a constant, because if you take the partial derivative with respect to y, respect to x of any y variable, it would be 0. So if that was x cubed y plus y to the 5th, the derivative with respect to x would still be 3x squared y. And we're not going to be focusing on that much. We're more interested in definite integrals. And let's look at this one when you have y squared 4 to y squared. So you see what you would do, you integrate that, you get the x cubed y, and you're integrating respect to x, so that's what you're plugging in for the variable there. So the y squared goes in for the x, makes it y squared cubed, and then put the 4 in there for the x, and you end up with this expression right here, y to the 7th minus 64y. So always keep in mind that when you're integrating respect to a certain variable, you can't integrate that variable at the same time. So if we were integrating respect to x, our limits of integration could only be numbers or y's, and if it's respect to y, it can only be numbers or x. All right, so there's the basic. Here's so you see this one with respect to y, the antiderivative of x squared dy would be just x squared y. Don't confuse that with derivatives, because it'd be like x squared might as well be 6 or something. Then it would just be 6y, and then 3y squared would be y cubed. You plug in the upper and lower limit with respect to x in for the variable y, where the y's are right there, which is what I did right down here, and worked this out and got terms that none of them combined. They were unlike terms, which is fine. Here's another one with y over x dy. Now, one of the things you've probably been taught, and certainly if you took Cal 1 from me, that's one of the things I scold people, never pull variable outside the integral. Well, when I said that, that means the variable of integration. In this case, because you're integrating with respect to y, x is behaving as a constant, so it's perfectly fine. You don't have to do that, but you could pull the 1 over x out at the same time. That's why that's correct. It would absolutely be wrong to pull the y out of there, because it's dy. All right, with that being said, the antiderivative of y would be y squared over 2. Plug in the x squared and the x in there for the y, and I just put the 2 and the x together, 1 over 2x. You get x to the 4th minus x squared. So you get this expression, whether or not it's distributed, who cares? Doesn't matter. But that's one correct form of the answer right there. Now I changed it down here. What if it was y over x with dx from y to y squared? Well, you could pull the y, which I did. I pulled the y out. I didn't have to. But anyway, the antiderivative of 1 over x dx is the natural log of the absolute value of x. So I put in y squared, I put in y, so it's y times ln of y squared minus ln of y, which I put a check mark here to indicate that that's correct. But sometimes when you see answers, they'll use log properties, so it's always good to be familiar with your log properties, meaning that because we're not squaring the log, it's acceptable to have that 2 brought down. And ironically, when you do that, you get 2 ln of y, then you actually have 2 like terms. 2 ln of y minus ln of y would just be ln of y. So not that answer is perfectly fine with a check mark, but you most likely might be looking at a more simplified answer. All right, basically we have now the integral of an integral, which they refer to iterated integral or whatever, but Might as well start calling it double integrals because that's what it's going to essentially be. So we can kind of not worry about the terminology iterated integral. Anyway, now this is important to be very, very, very careful here. Now, there's two possible orders of integration for these double integrals, assuming the variables are y and x. You can go dy dx, which means you can integrate with respect to y first, then x. You work your way inside out. And over here, it would be dx, then dy. Now, what's very important here, if your inside limits in this case are dy, the only thing that's allowed in here, now they have g1 of x and g2 of x, but those could be constants. But that just means you either can have two different functions of x, one different function of x and a number, or they both could be numbers. You cannot have y's there. Now, this is also very important. Your outer limits of integration are always going to be numerical. In fact, these problems are going to have numerical answers. I know those iterated single integrals I did earlier had variables in the answer, but if they were double integrals, we would have put numbers in there and the final answer would have been numbers. So you come over here, and so if your dx is on the inside, you go from h1 of y to h2 of y, meaning those are allowed to be y variables or constants, and then they must be numbers on the outside. The a and b kind of refers back to Cal 1. A and b, is the way they labeled it on the x-axis for your integration, and c and d was always the vertical values. So that's consistent. So that's we call the ones inside limits of integration, inside, then work your way outside. So let's see what this is all about. Now, I'm not going to spend a ton of time on the mechanics because as we go through this, you're going to see the most challenging part of this a lot of times is the setting up of problems. Now, this is just an integral thrown right at you here, so you just work it out, but you're going to see how we're going to be looking. They're going to define regions of integration, and then we have to figure out how to set it up from there. Okay, so notice you have this function right here, and it goes dx dy order. So if that's dx on the inside, notice that those are y variables, or they could be numbers, but they could not be x's. So you integrate this with respect to x first. So the antiderivative of 10 with respect to x would be 10x. 2x squared would be 2/3 x cubed. And then 2y squared would be 2x y squared. And then, you put your vertical line there to represent, then you're about to plug your limits of integration in. So I'll just show you real quick here. So this 2y is going to go in everywhere there's an x right there where I'm pointing. X, 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 2y, 2y cubed, 2y for that x, minus, the fundamental theorem of integrals. Oh, don't want that. Means it'll be subtract. Then you put y in there everywhere you see an x, 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 y, 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 and now we have dy. So you have a whole mess of y's there. I might have combined like terms if I had any. Yeah, so you see what I did? I kind of worked that out, and then I saw I had some like terms just so I didn't have to. It's kind of silly to do the antiderivative of individual terms if you can add or subtract them together. So I was able to reduce this to 10y plus 20/3 y cubed. Now we take the antiderivative with respect to y. We'll get 5y squared, and then y4 over 4 makes that. Let's see. Did I do something wrong here? It looks like there might be something wrong. No, I'm sorry. No, y the 4 over 4. Okay. 20 divided by 4 would be 5. All right. That's good. Because I didn't think I messed up because this is the maple answer right here. So probably means I'm all right. Put in 2, put in 0, put in 2, you'll get this result, and 0 will be 0. But there are some functions you have to be careful, like if you have e to the x or e to the whatever, or if you have cosine. Those are two values, when you put 0 in there, you don't get 0. But when they're just, polynomial variable terms like this, 0 will automatically be 0, so I just didn't write minus 0. So you get 140 over 3. So mechanically, these aren't too bad to work out. fact, one thing you could do is once you get it set up, if you want to use the numerical technology such as the FNInt and the TI-84 or something like that, I guess once you get this part done, you could put that part in the calculator and do the last step. But obviously the part involving the variables, you have to work out the integration there. But you could do that last step using technology. Okay, here's some pictures of different possible regions of integration that we call R. Triangle, can't really, it could be like a parabola more than a circle, obviously. Square / rectangle, because I can't tell for sure it's supposed to be a square or not. And then just some shape there, you know, this curve cutting through those vertical lines. All right, so once again, I'm reminding you then that the outside limits of integration are always numerical. All right, now, so this is where it gets interesting, is when you're setting up these regions of integration, you're working your way inside out, and the way you want to think about this on the inside is if it looks like something is varying, changing, the only things that'll be fixed would be vertical lines or horizontal lines. Anything else would be changing, therefore you would need a variable, with the restriction that the outside limits of integration, of course, are always numerical no matter what, whether it varies or not. So let's take a look at this. Now I'm just using an arbitrary f of x, y here, and we'll see that, you know, come up later where there'll be functions there. Now one thing I probably mentioned down here, let's see, well, I'll go and mention it now. If it comes up again, that's all right. But anyway, if there's no f of x, y, if you're just integrating, for example, dy dx with these limits of integration, you are basically finding the area of that triangle. That's what it would boil down to. Well, this one then we would know, obviously, if this is right. Okay, so we're looking at a region bounded by y equals 2x, y equals 0, and x equals 3, which is that triangle I have shaded in yellow. All right, here's how you want to think about this. I did dy dx first. For dy, you're looking at the boundaries here vertically for y. The lower to the upper. Lower than upper. Now in this one, the lower is fixed as being the x-axis, so that y value would always be 0. So that's what makes this 0 right here. But notice on the line, the angled line right here, y equals 2x, the y value is different as you move along, correct? In fact, it's defined as 2 times x. So the y would be 2x. So dy would go from a fixed 0 up to 2x, right there, to that line right there. Now, dx would always represent from left to right. Left to right. Now, you know, you might look at the line and go, well, the left side is varying. Yes, that's true, and we'll deal with that here in a minute. But considering that the outside of limits of integration must be numerical, you literally look at this as what's the smallest x to the largest x. So this goes from 0 to 3. 0 for x here at the origin, 3 right there. We go 0 to 3. So that's a double integral that would set up for this triangular region in terms of dy dx. Now how about dx dy? Now, so here's how you got to look. This means you look at this as going from left to right first. However, it's the same, the left is that angled line, but I can't use y equals 2x because, as I said earlier, when you're integrating with respect to a variable, the limits of integration cannot be that variable. So what we have to do, which isn't mathematically complicated here, fortunately, is we just take the equation y equals 2x and solve it as x in terms of y. So that would give you x equals y over 2. So going from left to right, so we are at this angled line, we're defined at y over 2, but on the right we have a fixed line right here. In other words, x would always be 3. It's a little crooked there, but obviously that was defined in the problem right here, x equals 3. So you're going from left, y over 2, to right being 3. Now vertically, outside limits, dy. Okay, you strictly look at this lower to upper, and once you're in the outside limits of integration, you are only looking at numbers. So we're going from 0 to the top one right here, which would be 6. I didn't label that as 6, but obviously if x equals 3 and y equals 2x, then that's definitely going to be 6 right there. So it's going to go from 0 to 6. Now, if we, like I said, if we evaluated those, let me see if I have done that. Anyway, well, okay. Oh, yeah, I did them down here. Okay, I'll talk about that in a minute. But I just put, to sort of, one way to verify it, well, I put in just some random function that I made up. But the idea is if you put the same function in there, the idea is both orders have to yield the same result if they are set up correctly. So, yeah, if this didn't yield the same answer, see, I put the same function in there and did my dy dx limits, and then over here, same function dx dy, and you see they match that weird answer. I don't anticipate you ever having a problem that comes up with a fraction quite this bizarre, but you are using calculators, so if you had to convert it to decimal or something, that would be okay. But as I was saying, then yeah. So to find the area of a region in a plane, you don't have a function in here. Your function's essentially just one or whatever. It's either dy dx or dx dy. Now I'll go back up there. If you look at this triangle, now of course we don't really need calculus for the area of a triangle. It's just 1/2 times base times height. So there's no doubt the area of that triangle, base of 3, height of 6. 1/2 times 3 times 6 is 9. And down here I worked out both of these integrals and dy dx for that one and got 9, and then dx dy for this one and got 9. So pretty easy. Like for example, the antiderivative of dy would just be y, so you put in 2x minus 0, and that gives you 2x, and the antiderivative of 2x would be x squared. 0 to 3, 3 squared minus 0 squared would be 9. And then the same one down here is just a little more involved because you have a subtraction step here, but it yields the same result. 9 represents the area of that triangle, so pretty sure that these are set up properly. Now let's see what this one says. Write the region of integration in both orders to find the area between y equals 1/2 x and x equals y equals the square root of x. All right, so I guess you could use some sort of calculator function to get this, but it never hurts to do a little math every once in a while. So what I did is to get the values of x where they intercept, I set these two equations and solved them. And like I said, you probably would have figured this out without doing this. But 0 and 4 are the values here for x. And then obviously it would be 0 to 2 for the y, because you'd have the square root of 4 right there. All right then, so dy dx, we would look at this from lower to upper, kind of where I have that vertical line right there, lower to upper, and it's a visual process here, so it has nothing to do with which function has the larger power or anything like that. Literally on this graph, the lower function is the line, so 1/2 x would be your bottom function. The upper function would be the square root of x, the curve. So you go from lower to upper, and then dx means left to right, strictly numerical. So you'd go from 0 to 4, no variables involved on the outside. All right, so you work out the antiderivative, pretty straightforward, easy power rule. Antiderivative x to the 1/2 would be 2/3 x to the 3/2, and 1/2 x would basically be 1/4 x squared. Put in 4, put in 0. Which means you only have to put in 4 for this one. You'll get 4/3. That looks about right. Now let's look at the setup for the other way, dx dy. Before I scroll down, you see what I did right here? Because if we're going dx first, which when I scroll down, those have to be y variables. So remember, you can never integrate with the same variable, the same limits at the same time with the same variable. So dx means they must be in terms of y. So pretty easy algebra to solve these. X equals 2y, x equals y squared. But this, like I drew this line right here, we are now reading this from left to right. And I'll scroll down and show you the answer here in a second. Left to right. So left is the curve. The curve would be x equals y squared. The right is the line, which x equals 2y. So it's going to go from the lower limit is going to be y squared, the curve. Upper will be 2y, the line. So y squared to 2y. And now dy means we're looking at it lower to upper, numerically only, 0 to 2 right there. Perfect. So once you have that set up, easy from there. You'll get 2y minus y squared, easy antiderivative, and it yields the same answer, 4/3, which it's certainly better, or something was either set up wrong or calculated wrong. But it needs to match. Okay, so I just put another function, let Maple do that. I just put another function in there, and so like I said, even if it's whether you're just integrating dx, dy, dy, dx, or some function, it still needs to be the same answer. And it looks like I went through the mechanics on this one. I think I'll skip over this just to save time. If you ever have questions, you can email me or something. And but it's pretty straightforward. I find a lot of students in these problems, it's not, the mechanical part of this isn't too bad. It's kind of tedious, but. And I got 136/9 working it out the long way, so same thing as as Maple got right there. I didn't do both. Looks like I didn't do both, which I didn't need to. I just did dx, dy. All right, now let's take a look at this one, this example. And we're going to talk about reversing limits of integration here shortly, but this one's okay here because we would be in a world of hurt here if dx came first and we had to integrate the square root of 64 minus x cubed. That would be kind of not doable. Well, maybe with some serious technology. But anyway, but in this order, it's not too bad because you just do dy first. So the antiderivative, so that treats all this stuff like a constant. So antiderivative of dy is just y. Then you put in x squared, put in 0. So x squared minus 0 makes it x squared. And so we come down to this, and getting that x squared in there, that was key for this problem. That was very important because now that created a problem that was designed to be u substitution. So, obviously I'm not going to give you something that cannot be solved. So you would expect something like that to happen. And so going back to u substitution from Cal 1, we have u equals 64 minus x cubed. du is negative 3x squared dx. So you have the negative 1/3 du represents x squared dx. I'm a big fan of changing the limits of integration. Big fan. Because that way I never have to go back to the original variable again. So I put in u of 4. I'll get 64 minus 64 is 0. And then I put in negative 4. 64 minus a minus 64 is positive 128. So I have a negative 1/3 on the outside, 0 on top, and 128 on bottom. Now, this I wrote this over to the side just to show you, but you'll see me do this a lot on the notes in this chapter. So hopefully now when that comes up, you'll recognize it immediately. Now, it's not something you had to do to solve this. But there's a property of definite integrals that says if you reverse the limits of integration, that creates a negative sign. So if you have a negative sign there, reversing those creates a negative sign, which then gets rid of that negative. So I just like to get rid of any extraneous negatives so I don't make any mistakes. Less likely to make a mistake, the fewer the negatives. So I reverse those, which kills that negative, makes it 1/3. And we have 128 and 0, u to the 1/2. Now I just have a power rule. I never have to go back to x again. And antiderivative would be 2/3 u to the 3/2. I'll put in 128. So that gives you a 2/9 with those fractions. 128 to the 3/2. I put the flag there indicating that that's correct mathematically. But, you might get a different looking answer because you can break this down from a radical standpoint, which I did right here. You see, that's what Maple did, simplified it. Now, of course, on an exam, if it was multiple choice format, you could use, the decimal equivalent. You could just see which is the right matching decimal answer. Or if it's a handwritten exam, you just can leave it just like that answer where the flag is. Anytime I put a flag, that pretty much means that's correct. But if it was multiple choice and you were trying to get a decimal answer, you could then take this answer, come up with a decimal, and then look at the answer choices, and you would see it matches that result. Now, we're not. This is just getting started now, practicing on how to reverse the order of integration, how to set it up. Now, this one's a little tricky, which is kind of tricky in general. But this, yeah, you don't want to integrate it the other way. So I graph the original function y equals x squared, and then boundaries. So you use that. So y equals x. So you see it's going from 0 to x squared for y, and then x is going from -4 to 4. So I kind of shaded this picture. Now, because to go dx dy, we're going to have to write this as x. As x, you can't just say x equals the square root of y, because technically, when you're to the right of 0, that would be true. X is the positive square root of y. But to the left of 0, it's x equals negative square root of y. So that when that kind of situation happens, and we'll see this come up again, that sometimes double integrals in one order have to be written as two orders, or two double integrals to represent the same region. So that's sometimes makes it more challenging. Of course, this one would be not doable anyway because of the dx first, but still, this would be the right way to set it up. So you would look at it going from left to right of the left part of the negative side, where it splits at 0. So on the left, you have -4. On the right, you have the left half of that curve, which would be negative square root of y. And then vertically, you're going from 0 to 16, y equals x squared. Then we start at on the other side of the origin. You're going to go from left to right, the left to the right. Left is now the curve, square root of y. Right is 4. So you're going from square root of y to 4 and 0 to 16. So it's actually the sum of two double integrals to represent that other double integral. And we're going to see some more of this shortly. This one, I don't know. This one's very similar to that other example I showed you. It just has x to the 3/2 and so x to the 2x. So I'll kind of skip past that one. But if anything, reversing the order of integration might be good to do without worrying about working out the details, the setup of it. So this one goes lower to upper, x to the 3/2 on bottom, 2x on top, and then it goes from 0 to 4 on the x-axis. And you see I actually solved it there, but you probably could have figured it out without doing this. So to come down here and solve this, you see what I did right here. I had to reverse, solve for x in terms of y. And so x would be y to the 2/3, and then the other x would be y over 2. So going left to right, the line is on the left, the curve is on the right. So x would be y over 2 on bottom, and then the line would be x equals the line y over 2 to the curve y equals 2/3 right there. So the line's on the left, the curve's on the right. And then we go lower to upper, which will be 0 to 8. The reason why I know it's going to be 8 because when x is 4, 4 raised to the 3/2 power, square root of 4 is 2, 2 cubed is 8. And I worked it out up here and got 16 over 5, but then I didn't work it out. I could have, I just didn't. But I just let Maple do it to verify it was 16 over 5. So that's a good chance that probably means my setup is correct. And now this next example, so you see there's with an f of xy written right there. That just means there's not going to be an actual working out of an integral here because there's no variables to integrate. But once again, it's real good practice on setup. Now let's say, okay, now to graph this, and certainly you can use a graphing calculator. I'm going from square root of y to 2, so if I have x equals the square root of y, I would want to rearrange that to use the graphing calculator, y equals x squared. And so there's that curve, and we know it's bounded, x is bounded at 2 right there. You can really see the marks there, and then y is going from 0 to 4, so I just drew a little line at 4. Now what's interesting is, if I draw that horizontal line at 4, vertical at 2, and then that curve in there, you have to really be careful how this integral sets up because it is possible that the shading could have represented this area right here where I'm moving my cursor. It could have meant that part above the blue line right there, above the blue curve. Now, let's talk about how I knew it was this bottom and not that top. All right, fair enough. It's because the region helped me graph it, but to know which part it would have been is that if x is going from the square root of 2 to y, that means the square root of y would have to be on the left, and then 2 is on the right. Because the 0 to 4 doesn't tell you anything. Because the 0 to 4, if I shaded that other region, 0 to 4 would be the same outer limits right there. It's 0 to 4 both ways, but it's inside here. So the left function is square root of y. The right function is 2. So square root of y to 2, that's how I know it's that bottom region. So let's see if I didn't, but let me go ahead and mention that. I thought I had that in the notes here, but I don't. But let me mention what would it have looked like if it was the other order. All right, fair enough. It would have looked like this. Going left to right to represent this region right here, I'll just kind of shade it like that. I would have had, let's see, this would have been 0, representing the y-axis, and then it would have been to the curve. So it would have been 0 to the square root of y, and then still 0 to 4. So that's what it would have looked like had the regions was supposed to be what I just shaded in there in red. If it was supposed to represent that region, that's what the integral would have looked like. So obviously you got to be careful with that. All right. Okay, so get rid of that now. Now I wanted to reverse this to dy dx. So I already had y equals x squared for graphing purposes, but we would have needed to do that anyway. Because now when you have dy right there on the inside, you can't have y's in your variables. So now I look at this dy first. I go lower to upper. 0's on bottom, and the upper is x squared. Upper is y equals x squared. So it goes 0 to x squared, and then dx represents left to right will be 0 to 2. And then that's how we'd reverse it. Okay. Now, don't know why that was down there. So here's another one, sketch and switch, because like I said, that's really an important skill. That often gives people more trouble than the actual integration does. You have to pay careful attention. So I graphed, I took the right here, so y is going from 0 to 4 minus x squared. And there's the blues, the 4 minus x squared. So the fact it's going from 0 to 4 minus x squared would mean that it's going to be that inside shading for sure, and not that outside shading. And we do know that y will go from 0 to 4, and x will go 0 to 2 numerically. So it depends on which order of integration you have. So the given problem, 0 to 2, means right here on the outside. So that's how I know it's on the inside, going from 0 to 4 minus x squared. The other part right here would have been if it would have gone from 4 minus x squared on bottom to 4 on top. That would have been the other shaded region. Okay, to switch this, I had to solve for x in terms of y. And this isn't like that problem I had earlier with the parabola and the two separate regions. We're only dealing with half of it there. So x is the positive square root of 4 minus y. I don't have to worry about plus and minus like I did earlier. So we don't have to worry about the positive half. So you look at the shading and you go, okay, left to right. Left's going to be 0. Right's going to now be right there, the curve, the square root of 4 minus y. So 0 to the square root of 4 minus y, and then y vertically would go from 0 to 4 numerically. All right, let's see what this one is. Switching them again. And we have, cannot get this to cooperate. Let's see. There we go. Go up a little bit there. So let's see what this says. We have all right, so you're going from y squared to the cube root of y for x, and then 0 to 1. So I've graphed them, and the blue one you can see from the color coding right there, it's your x cubed, and then the square root of x. Oh yeah, because I had to solve both of them. So if x equals cube root of y, that's the same thing as y equals x cubed. And if x equals y squared, y would equal the square root of x. Once again, only the positive square root of x, because we're not crossing over the y-axis. So there's no negative side here. So you see, it's this one the shading's kind of obvious because you have an enclosed region. But anyway, left to right, see the left to right, we have the x equals y squared, which is y equals the square root of x in red. That's on your left. And then x equals cube root of y equals x cubed. That's on your right. So then looks like I worked it out this way, which is not a difficult one to work out. But let's see if I should have reversed it. Yeah, there's the reversal down there at the bottom. And well, let's look at that setup. In fact, I could just put this up here. I didn't like my... So let's see, let's just mainly look at the setup more than working it out. I think you'll be able to work it out just fine. I just draw this myself. So you look at this, we're going now, dy means lower to upper. So y cubed, y equals x cubed is on the bottom, and then the square root of x is on the top. So lower to upper, and it's also going to be 0 to 1, because those are the both limits, both horizontally and vertically. So I think I'll just bring this up here. And just kind of copy the answer and I'll just write the answer. And let's see. And then we'll just say equals 5/12, which I obviously did work it out, but figured just to make it more efficient there, I'll just leave that part out, and that way we can see the entire problem on the same page. All right. Okay. All right. So let's see, what do we have next here? Let's see. Now, sometimes, reversing the order is a skill we've been looking at, just to be able to do it. But sometimes it's absolutely necessary. Now, this is a problem I'm very famous for asking on an exam, so this would be a good one to know how to do. Now, you might look at this and think is some sort of integration by parts might work here or something. No, it will not. So you see the issue here. It's necessary to reverse the order because with that e equals negative y squared, we need some sort of y there to be able to do substitution. So we're kind of stuck right there. I think there's some advanced integration techniques that I think can work that out, but not anything that we certainly need to worry about. All right. So first thing I want to do is sketch the picture. So I have, once again, the order is important. I have y equals x to y equals 2. So I have y equals x, and then I know we're going to y equals 2, and then x goes from 0 to 2. So that's what, so once again, you got a line, and you're not sure which of these two regions it could be. It's those inside limits of integration that tell you. So if you're going vertically from x to 2, x to 2 means it would be that region right there. Now let's reverse this, dx dy. So if I'm reading this from dx dy left to right, I would be going from the y-axis to the line. So obviously now we have to change the variables, and this one's really super easy because if y equals x, that means x equals y. So we'd be going from 0, and we're changing right there, so x would be determined by y, 0 to y, and then still 0 to 2 again. It is y, but all right. Now this helps us because now there's no, the antiderivative dx will just be x. We don't have to worry about that e until the next step. So that x, then you go y minus 0, that will bring you the y in there. So that was very, very important because that now turns this into, a U substitution problem. So that's why this was important, because like I said, not only reversing the limits of integration was absolutely mandatory to be able to solve it. So now I have that y there, very important. So if I let u equal y squared, negative y squared, I'll get negative 2y dy for du. I didn't show the negative 1/2, but obviously the negative 1/2 comes out there, and there it is right there. And then I have e to the u du, so you put in 2. You got to be careful here because that's not negative 2 all squared. It's the negative of 2 squared. So it would be negative 4, not positive 4. 0 will be 0. I have negative 4 on top, 0 on bottom. You see I switched them right here to get rid of that negative. Not that that's the only reason. I didn't have to. Could have done it without it. I think it's easier. Once you get in this form, e to the u du, that's about the simplest thing you can have because that's just e to the u. You don't have to even worry about the plus 1, anything. That's really easy once you get it to this form. So e to the u, you just put in 0, put in negative 4. It's probably good to know that e to the 0 equals 1, especially if you're trying to pick out answers. That certainly would be good to know. But I guess technically if it was handwritten and you had e to the 0, it wouldn't be wrong per se, but always good to replace e to the 0 with 1 whenever you can. All right, so let's see what Maple said here. I do believe that's the same as my answer if you distribute out the 1/2. I think we're good. Fantastic. Now this one. Yeah, so it's, we saw one earlier that where it was a single double integral and then it turned into 2 double integrals by reversing the order. So it's possible that so we've seen that. We know that it can be 1 double integral one way and 2 the other. It can actually be 2 double integrals both ways. We'll see that too. That's certainly possible. But this is going to be interesting because it's actually going to turn into only 1 double integral if you switch the order. Now to graph this. Oh, I already have the answer there, don't I? That's all right. I'm going to explain the steps to you here. Okay. Okay, so to graph this out, we have you just kind of treat it as two separate pieces, and they are going to connect. That's kind of what makes this whole thing sort of work out the way it does. They connect. So you're going from, y is going from 0 to x over 2, 1/2 x, and then x is going from 0 to 4. So I know I have this triangle right here. Lower to upper, 0 to x over 2, 0 to 4. Well, conveniently enough, when you go over to this side, going from 0 to 6 minus x, when you put 4 in there for 6 minus for x, 6 minus 4 would be 2. So that's what's guaranteeing in this case that line is going to connect to the other line. So that green line right there is your 6 minus x line. And then it's telling you here, how do we know where that stops? Well, it says x goes from 4 to 6. So they meet, so when x is 4, they meet right there at that 2. And then when x is 6, we have 0. So then it goes right back to the x-axis. Now, I'll show you, look at this visually. If we were just looking at this picture and just had the equations and weren't looking at the original double integral, how would I know in dy dx by looking at that picture that it would require two double integrals? All right. Well, what you're looking for is in your region for dy dx, if it's not going lower to upper, if the upper functions change at any point, which we had that earlier actually with that parabola, negative side, positive side. This isn't the same issue, but anytime your upper function changes, it's going to require more than one double integral. And I'm not going to do one with more than two double integrals, but theoretically, I guess it could be. So you see that the upper function is this purple line right here, and then right there at the dot, the upper function changes. So it's two different uppers. So you got to go lower to upper, and then where it splits off where I drew the red line, you got another lower to upper. That's what's representing both of these. Now, the other order, it's only going to be one double integral. And here's the reason why. Because you're looking at this left to right. Now you see where they change over right there. Forget that vertical red line. That don't include that in the way we're setting this up. But when you're going left to right, there is when they connect here, there's only one function on the left is the purple line, and the green line is a function on the right. So you only have one left to one right. There's a left to a right. It doesn't change rights. In other words, like let's just say hypothetically that if this maybe, I don't know, did something like that. Or, well, maybe not that. That's not good. I'll draw it. And you'll see, maybe if it came down vertically or something, it connected, and then this graph still kept going down that way. Then you would have two separate right functions, this green line and the vertical line. Then you would have to split it up. But this one has the same left and the same right. So I've got to solve for x in terms of y. What does that give me? So I have x equals 2y on the left, so it's the lower. Y equals 6 minus x becomes x equals 6 minus y when you solve it, so it's on the right. So it goes 2y to 6 minus y, and then vertically, dy, 0 to 2. 2 is the y value. Now I put the original double integral. Once again, this is just a triangle, so actually pretty easy to verify if we got it right or not, but because the area of that triangle would be 1/2 times 6 times 2, which is 6. So this original setup yields 6, and then I'm going to kind of skip past this part right here, but that's just the working it out. But anyway, I worked out my result that I just set up, the new result, and it came out to be 6. So probably means I set it up correctly. It would be kind of weird if 6 isn't exactly a fluke number. Sometimes you have to be careful if an answer comes out to be 0 or something like that. You could have made a mistake. But with 6, it's probably not a mistake. Let's see what we have here. Okay. Oh, something didn't come along for the ride here. What in the world? should be y equals, okay, I don't know what happened here. Oh, probably y equals x, and then what's the bottom y? Y equals 0. Okay, that's probably what it is. I don't know where that 0 went. All right, write it in here. And so we're going to set up the integral in both orders. Oh. So we have the function x times y equals 9. And so that's the same thing as y equals 9 over x. Set up a double integral of both areas. I didn't bother to work out the integrals. I think, or maybe I put them in maple. We'll see. Oh yeah, I did. I put them in maple. Okay. Just to verify. All right, so let's look at these graphs carefully. Y equals 9 over x in the first, so we're bounded by y equals 0, y equals x equals 9. There actually is another part of that graph that goes in the third quadrant, but for negative values, but we're not concerned with that. Now this one's interesting because it actually does require two double integrals in both orders. Now let's look at dy dx. Now similar to that last one, we go lower to upper. Two different uppers. Right here at 3 where they split off, because 9 divided by 3 makes that 3, and obviously you could have put x in there for y and solved it. X squared equals 9, x equals 3. So that's where it splits off, lower to upper. So you got to go to the line first and to the curve second. So this would set up as like so. So the left one is the left triangle part would go from 0 to x, 0 on the bottom to x here, and then 0 to 3 for the x-axis. That represents the triangle. Now for this part of it, lower to upper would be 0 would be the lower, 9 over x is your upper, and then for x, I'm sorry, you're starting at 3 and you're finishing at 9. That was one of the given boundaries in here. X equals 9. So x is going from 3 to 9. Yeah, because actually that graph 9 over x is never going to touch the x-axis. Granted, the limit of it would be 0 as x goes to infinity. But remember, limits don't have to always equal what you're, So as it approaches 0, it never hits it. Now this one's a little tricky. That's kind of why I was drawing that sketch earlier with that vertical line a minute ago. This one's a little trickier because it might look like it's the same function left to right. And if that curve actually came down and was hitting the x-axis right there at 9, if the curve was hitting right there, then it would just be one double integral. But it's not. The curve comes down at 1. When x is 9, y is 1. And you can see that easily, right? Y equals 9 over x. So it's 9 at 1. So you actually have the same function on the left, which is the line, but you technically have two right functions. One of them is that short little vertical line right there at 1, and the other right function is that curve. So here's what this one would look like. So we're going from, so if y equals x, that means we have x equals y. We are going from y I'm doing the bottom part, bottom part first, y, and then x is going to 9. See, that's a fixed value for x. No variable there. Y to 9, and then that little horizontal line right here means y is going from 0 to 1. Now we're focusing on that region of integration above this line, which you see above that line, you have the same left, you have the same right, left to right. So left is the same y right there as on the left, and then 9 over y, which is just resolving y equals 9 over x. 9 over y is your right function, and then lower to upper would be from 1, where the line's drawn right there, to 3 right there at that point. So y would go from 1 to 3. And I put both those setups in Maple. And both yield the same answer, 9 halves plus 9 natural log of 3.